So I just wanted to go through at a little slower pace the adaptive management pilots, maintenance, and expectation management lecture that we touched on towards the end of the workshop. The main point is to reiterate that realistic expectations are critical, and we've discussed this over and over and over again during the workshop. Remember, we're relying on pretty simple techniques and sometimes rodents and sticks. So don't take too narrow of a focus on individual dams or one dam complex. Take that broader view, like we talked about a bunch of the whole system and the dynamics that come with these things being transient features on a landscape. The beaver and the wood that make up the structures, they come and go, and with that we get dynamism, and as we pointed out in the earlier lectures, we get a lot of the habitat heterogeneity that we're seeking to restore. How quickly this happens, how instant that gratification, depends a lot on the metabolism of the system you're working in and its physiographic setting. So some of these flashier systems that we're scared of in a lot of cases actually are places that we can see that quicker. We need to expect the unexpected. Don't just plan for what you hope for, but plan for what you're not expecting but is plausible, could happen. But there's a big difference between that and what is implausible, and the things that are implausible can be clearly defined. If you're looking to beaver to do some of your maintenance, how vulnerable is your project, and particularly the beaver, to predation, poaching, etc. And if you have an invasive problem, you probably have an invasive problem. So one of the ways that we think is a really helpful tool for dealing with this expectation management is adaptive management. This is an example from Steve Bennett and Nick Bowis and I from the fisheries article that covers the SOTN project that Steve Bennett presented on. And this is the classic adaptive management loop. There's the planning, the doing, evaluating, through monitoring, and then potential adjustments to either your plan or what you do. And so this is why adaptive management is referred to as learning by doing. If we take the SOTN, that high density large weight debris project, as an example, basically the problem there was poor wood and riparian conditions that were limiting the provision of energy and predation refugia, pool habitat, and ultimately salmonid production. So that was the sort of identification of the problem. The goals and objectives were laid out, and along with that, some ecological concerns and testable hypotheses. So we established baseline data and some indicators to compare against. We developed experimental design monitoring restoration plans, and we came up with a pilot for what we want to do. I'm going to talk about pilots in a moment. We implemented those pilots, and from that, and the monitoring of that, we were able to make adjustments to our full implementation plans that were implemented in phased treatment over a series of years. And each time, we were getting a little bit better and adjusting how we tackled that. We had annual monitoring in this case, and periodic system-wide evaluation, etc. So this is an example, and even though this is an example in the context of an intensively monitored watershed, which Steve talked about, where the IMW and the monitoring, all that can be quite expensive, what we're trying to argue is that the actual implementation of adaptive management can be done really, really cheaply. A lot of this starts with that clear identification of objectives. Why are you feeding the system structure? If we're working off this structural starvation hypothesis, what's the impairment that you're trying to address? Here's sort of a laundry list of things that we talked about. Clear goals will lead to better designs. This is from Nick's work on Bridge Creek, where the idea was that if we had more beaver dams, that would increase water levels, make more pool habitat for fish, increase the thermal refugia for fish, increase flow complexity, which would lead to deposition and erosion, leading to habitat complexity, increasing of sinuosity gradient, increasing floodplain connectivity, increasing the riparian extent and ultimately the food supply for beaver, building resilience for those dams, increasing the ponded area, making more predator refugia for beaver, and ultimately making more beaver dam colonies. So this was very specific, hypotheses here, and to be clear about what it is you're trying to achieve. We have a bunch of examples. These are linked here individually, and then also on the website of adaptive management plans that we've prepared for urban settings, for ranch settings, for municipalities, etc. And so you can take a look at those, and in this fisheries paper, we kind of we go through and lay out how to implement these adaptive management plans in an affordable fashion. Okay. A lot of that in terms of coming up with ideas, it doesn't have to be things you invent on your own. Just point where in the literature you're borrowing that idea from, and if you need to make a tweak to it, make a tweak to it. Here's a classic from Naaman that just the sort of while there's beaver activity, they follow these sort of successional patterns where you've got a stream that can turn into a pond or a new pond. Eventually, there's your active pond. Here's your older pond, but it can revert back to a meadow. So this is sort of this reversible succession. Versus at some point, these things can turn into emergent wetlands, bogs, the so-called beaver meadows. Another example, here's one where we kind of tweaked a concept that we thought was relevant, and it is relevant to a lot of these things. This is sort of a state and transition model where the vertical axis represents the degree of channel complexity and or incision. And so up here, high complexity, low incision, down here, low complexity, low incision. And what we have is a situation or in the pre-project where we had reaches that were locked down in this low homogeneous sort of bowling alley state. And anytime you'd have a disturbance or a flood event, it might push the system up onto this precarious little ledge, but its tendency is just to fall back into that degraded state. And so really our hypothesis was, well, historically, this thing would have dynamically switched, in those sort of stage 0 connected floodplain habitats between different but stable and resilient habitat states. And so what we're trying to do with these structures is build up a levee, so to speak, of energy that keeps it from falling back down in this degraded state, that builds some resilience, but allows for dynamic switching between these different states. Okay, so that's out of one of our early design manuals, design reports, and it's also a version of that is reflected in the fisheries article here. One of the details in terms of how we do these adaptive management plans is we have a couple of specific loops that come in this evaluation monitoring phase, and this doesn't have to be expensive monitoring. This is really just to decide whether or not we're proceeding as we expect or not. And so really right here we have this hypothesized pathway, and what we expect is we come in annually and we look and we ask, is this whole complex of structures I put in achieving its objectives? And we expect that yes it is, but in a lot of cases the functional lifespan won't be over, but then at some point it achieves a desired dynamic stable system state, i.e. it achieves this. That's what we're hypothesizing that we're going to get to. Of course, what we're allowing for is each year considering if it's not achieving its objectives, is it causing harm? And if not, we can if it is, we can remove the complex or make a tweak to it to mitigate that harm. If it's not causing harm, are new opportunities or risks apparent now that weren't apparent when the thing went in? And if so, if there are opportunities, you might expand or enhance the current restoration efforts. Or if not, you might just leave it alone, and that's where you'd exit out of that monitoring loop, and so you wouldn't have to do any adjustments. Whereas this right here represents an adjustment in that adaptive management loop. In contrast, if you looked at something and the functional lifespan of the dams was over, let's say in a complex, all of the dams filled in with sediments, filled them to the brim. Well, we might just leave, if the functional lifespan was over, yes, then hopefully we've gotten to this point where we've achieved our new desired system state. If we haven't, we might need to add structures on top of this. So this would be an adjustment that reflects a maintenance action. So maybe what we're hoping in this example is one meal gets us all the way to that self-sustaining state. But what this is allowing for is that I might need multiple meals to get me there, right? That would represent an adjustment. I could add another little thing in here that would basically signal that we're actually anticipating it's going to take multiple meals there first. But if there's still, if the complex is still functioning, then we can go alone. If we come over to this point where we're curious about, the individual dam, we can focus on this in a little more detail on an individual structure. And it's important not to be too reactionary. We have to recognize that some of the failures that happen are good and some are necessary. And so if we have, here's a beaver dam support structure or a reinforced dam, we can look at this, and if this is one of these, then we keep going down. If it's not, then it's a new beaver dam, and we look at it, and it has the potential to achieve objectives in a new beaver dam that we didn't build that showed up there. If yes, we might, in this case, decide to reinforce it with posts, and this is from Bridge Creek, if we're worried that it might blow out. If not, we just leave it alone. Similarly here, if we're dealing with one of our structures and we ask if it's achieved its objectives, and then we look at failure, this is, if there's minimal failure risk, we could leave it alone. If there is some failure risk and we don't want that, we could do some toe reinforcement with mattress and posts, right? So this is one example of, working through how you could make tweaks to individual structures. Some different examples, some more generic examples you'll find in both this as well as in some of these adaptive management plans, okay? We also have a design and monitoring app. We have a lot of different flavors of these actually. And these are really good for transparently documenting and articulating your design intent. They force you to explicitly say what your design hypotheses were. This is how, this is why it's an adaptive management, make it experimental. And we've got a little article that we wrote on this and kind of how these different forms these monitoring apps can take. I gave you a nice old school paper monitoring app to fill out in the field. And the questions are really important, but we also in these apps tend to record a design video, and those design videos can be really, really helpful for transparently laying out what it is that you're trying to do that's difficult to convey in a paper form or in just a series of checkboxes. Sometimes, pictures and videos are worth 1,000 words. Here's an example from an earlier, this is sort of, our post-assisted log structures, and we are basically showing this is what the design is intended to do. It's constricting it to make this constriction jet, right? And then these were the expected responses. And we had a reviewer came across and said, well, some of the structures will look okay during a couple of year or lower flow persistence, but then they're obliterated in the first bank floor slightly higher event. Well, literally as we got that review in, these structures that were built in a pilot were subjected to one of these higher flows that he said it should just blow this out. And that's the structure right there. And this is that eddy. This is that same eddy, that we predicted in a cartoon fashion should be right there. And these were actually working and holding up to modest high flows. You know, and so the fact that we had laid that out transparently, and you have some simple evidence through monitoring, that can be a really helpful thing. Um, this is another example of some of those design forms that we'll end up creating and filling out. And we just, you know, record basic things like, where is this going to go? What are we going to anchor the feature off of? What are we exploiting the existing of? Are there existing features we're trying to accentuate? And, you know, what is it you expect to do? What do you expect to happen? And so what doesn't fit neatly in there, in this form, we have a very simple, under the photo, we have a very simple little thing for what doesn't fit in there, just recording that as a movie. And so this is an example of one of these, and this won't be very exciting, but they are very helpful for capturing what doesn't fit elegantly there. So these really simple little videos can be extremely helpful in terms of capturing a lot of your thought process, and then as the implementation crew comes in behind the design crew, they can go ahead and build those, and you have those there in your record to sort of remind you what you were trying to do. Now, this may seem ridiculous when you're doing 5 structures or 10 structures, but when you move into the hundreds and the thousands of structures, it's really hard to keep track of all these. And so this is really a very handy way to kind of document what you're doing, and it can provide that level of documentation, which I wouldn't encourage in terms of an initial permit application, but I think makes a ton of sense in terms of the sort of post implementation documentation, as built documentation, as well as the design process. So again, the thinking is what's important, and the paper design that we provided you in your workshop handbooks. Those can be modified. You can make those as you want, and if you want to turn those into apps, there's lots of folks that can help you with that, including ourselves. Okay, it is important to think about the effort and resources that are going to be required, right? You know, are you doing the initial meal preparation, or are you sort of waiting for that to happen? Who's going to be doing the maintenance? Are you getting into the business of preparing meals for the medium or longer term? If so, be very clear that that's what you're getting into. How frequently is maintenance going to be required? It's okay if you don't know the exact answer, but take a stab at that and use adaptive management to see if you got it right or wrong. And then this is really important. When are you done? What's your exit strategy? We don't want to be creating sort of mini Iraqs. I guess what I mean by that here is, you know, it's one thing to kind of go in and start the whole restoration intervention and start feeding these systems, but identify what your exit strategy is going to be ahead of time. It's okay if you need to tweak that, but know what the goals are, come back to those objectives, and when can you consider, for example, Beaver having taken over that for you. I just wanted to show you one of our sort of learning experiences with pilots here, and this is from the San Rafael Desert, San Rafael River system. It's a system that used to be much more active, but due to changes in water development in the upper basin and the flow regime, and then introductions of tamarisk, an invasive salt cedar is another name for it, invasive species that's come in and caused the channel to narrow dramatically and be much less active, such that you have sort of a bowling alley there. And the goals here were to improve fish habitat, break up that bowling alley, and also remove tamarisk. And those goals initially were fairly isolated from each other. Basically, for the riparian and upland treatments, it was all about removing tamarisk, and then for the stuff on the in-channel, it was all about creating better habitat. So here's an example of a beaver dam analog that was very much built in the way these things were meant to be built, i.e. willow wicker weave, just like you guys did in the parking lot, and that willow was brought in from about 50 miles away. And this is a sand-bedded river. You can see here this gentleman is standing where sediment has deposited right to the brim of this thing, and this guy's standing in a nice big plunge pool down at the bottom. So this created some good habitat, but it was very costly in terms of time effort. Each of these dams took quite a while to build. It's a sand-bedded system, and they're building at slightly elevated flows, and it was pretty tricky. So, a little example of some adjustments, learning from this process. So, trying to fit these BDAs within the trench of this bowling alley. You could do okay for a little bit, but as those high flows pick up, a lot of these things end up not looking very much like channel spanning dams and BDAs. This is exactly why I'd argue you should consider a pilot as part of your adaptive management. Don't do your full implementation first. Identify what it is you're trying to do. Go out and try the things you think are going to work and try things you don't think are going to work. Now, even though this BDA structurally failed, and this one also had a little in cut, this one lasted. There was some problems with this one. These are providing some of the best habitat in terms of fish habitat on this heavily impacted river. And so what to do when you see this is recognize that actually it wasn't a beaver dam that was causing this. It was the failure of a beaver dam. Could I have gotten away with other structure that might have created this same sort of thing? And so we could look at this and say, oh, we did a horrible job and it failed, or we could say this is the best fish habitat we have yet. And in looking at it with that latter lens, we'd say, well, is there a quicker way I could have achieved that? Could I have just taken, for example, some of the dead tamarisk that was being removed off the riparian areas, chuck that in and use a couple of posts to pin it? And indeed, that's what we started doing out there to kick off this lateral expansion into and the erosion into some of the high surfaces, and then creating a more diverse array of elevation surfaces to grow inset floodplain vegetation on. We do a few treatments of this, and we save ourselves maybe it takes us 10% of the time to build some of those. Just like we saw in the workshop, this could save a lot of money in the implementation. And then later, once we have wide areas and some narrow areas and that variation in width, there might be some better opportunities for building some BDAs that actually spread out across these new inset floodplain surfaces. So that's really what we mean by trying to use adaptive management and pilots and learn from that, learn from your mistakes, learn from your failures, build things to fail, and learn from the logistics of doing that in order to buy yourself efficiencies so you can prepare bigger meals and throw bigger parties for these systems. Okay. If you have any questions with any of that, please do get in touch. But hopefully that provides a little bit more comprehensive overview of this than what we touched on very rapidly at the end of the first day. Thanks a lot.